Type of load: static loads are better tolerated than dynamic loads. Inclination of load: a vertically applied load is ideal, while inclined loads reduce effective soil strength. 7. Shape and size of footing. Square and circular footings provide higher bearing capacity than rectangular or strip footings. Larger foundations distribute load over a bigger area, improving stability. 8. Presence of adjacent structures, excavations or nearby buildings can cause stress interference, affecting soil stability. Deep foundations nearby may induce lateral or vertical pressure changes. 9. Seasonal and climatic effects: rainfall and flooding increase moisture content, reducing bearing capacity. Frost action: in cold regions, water in soil may freeze, causing expansion and reducing load-bearing strength. 10. Soil improvement methods. 4. Techniques like soil compaction, grouting, and soil stabilization enhance bearing capacity. Geotextiles or reinforcement in weak soils can improve load-bearing performance. Question 3. Explain the different classification of piles with neat sketch. Answers. Classification of piles. Piles are deep foundation elements used to transfer loads to deeper soil layers when surface soil lacks sufficient strength. Piles are classified based on various factors, such as material, function, and method of installation. 1. Classification based on material: timber piles made of strong wood like oak or pine. Used for temporary structures or in waterlogged areas. Vulnerable to decay unless treated with preservatives. Concrete piles: precast concrete piles, cast in a factory and transported to the site. Cast in situ piles: concrete is poured directly into a drilled hole at the site. Highly durable and resistant to chemical attacks. Steel piles made of steel sections such as H-piles or pipe piles. Used in marine structures and deep foundations. Require corrosion protection in aggressive environments. Composite piles. Combination of two materials. Used where the upper part is exposed to air/water while the lower part is embedded in soil. 2. Classification based on function: end-bearing piles. 5. Transfer loads to a strong soil layer or bedrock at the base. Acts as a column, carrying loads directly to firm strata. Friction piles transfer loads through skin friction between the pile surface and surrounding soil. Used when strong soil layers are too deep to reach with end-bearing piles. Combination piles carry load through both end-bearing and skin friction. Used in sites where moderate strength soil exists at depth. Tension or uplift piles designed to resist uplift forces caused by wind, water pressure, or expansive soils. Used in transmission towers, chimneys, and bridges. Compaction piles displace loose granular soil to increase soil density and bearing capacity. Common in sandy soils where compaction improves foundation stability. 3. Classification based on method of installation: driven piles installed by hammering or vibrating into the ground. Types: timber, steel, and precast concrete piles. Causes noise and vibrations, used in large projects. Poured piles: a hole is drilled and then filled with concrete. Causes minimal vibrations, used near existing structures. Jacked piles pushed into the ground using hydraulic jacks. Suitable for areas where vibrations need to be avoided. Neat sketch of piles. Below is a diagram illustrating different pile types. 6. End friction bearing pile. Strong soil or bedrock. This sketch represents end-bearing piles and friction piles. Question 3. Discuss briefly the method of estimating the individual and group capacity of piles. Answers. 1. Individual pile capacity estimation: the capacity of a single pile is determined based on two main components. End-bearing capacity, the resistance at the pile tip, calculated using soil-bearing capacity theories like Tertsagi's or Meyerhoff's formula. Skin friction capacity, the resistance along the pile shaft, estimated using the adhesion factor or friction factor depending on soil type. Total individual pile capacity is given by Q equals QB plus QS, where Q is the ultimate load carrying capacity. The safe load is found by applying a factor of safety. 2. Group capacity estimation. When piles are used in a group, their combined capacity may differ due to interaction effects. The group capacity is determined by sum of individual pile capacities. If piles are spaced sufficiently apart, the group capacity is roughly the sum of the individual capacities. Block failure mechanism. If piles are closely spaced, the group may act as a single block of soil pile system, and the failure mechanism is analyzed using soil shear strength principles. The lower value between the sum of individual capacities and block failure governs the group capacity. A reduction factor may also be applied for settlement considerations. Summary: individual pile capacity is estimated using end bearing and skin friction. Group capacity is the lower of the sum of individual piles and block failure capacity. Safety factor is applied to get the allowable load. Question 4. Explain Terzaghi's analysis for determining the safe bearing capacity of the soil. Answers: Terzaghi's analysis, also known as Terzaghi's bearing capacity theory, is a method used to determine the safe bearing capacity of soil by calculating the ultimate bearing capacity of a foundation based on the soil's shear strength properties and the geometry of the footing, considering a failure mechanism where the soil beneath the foundation is assumed to yield in a plastic manner, creating distinct shear failure zones. This ultimate bearing capacity is then divided by a factor of safety to obtain the safe bearing capacity. Key points about Terzaghi's analysis: assumptions. The foundation is considered shallow, meaning its width is greater than or equal to its depth. The soil is homogeneous and isotropic. The load is applied vertically and uniformly on the foundation. No sliding occurs between the foundation and the soil. Failure mechanism. Terzaghi's theory divides the soil beneath the foundation into 3 distinct shear failure zones. Zone 1. Soil at the edges of the footing experiences a passive Rankine state, pushing against the foundation. Zone 2. A zone of radial shear stress occurs around the footing. 7. 8. Zone 3. A central tension crack may develop under the footing depending on soil properties. Equation. The ultimate bearing capacity is calculated using the following equation, where C is the soil cohesion, gamma is the soil unit weight, B is the footing width, D is the depth of the foundation, and NC, NQ, and N gamma are bearing capacity factors depending on the internal friction angle of the soil. Q equals CNC plus QNQ plus 0.5 gamma BN gamma. Calculating safe bearing capacity. To determine the safe bearing capacity, the ultimate bearing capacity is divided by a factor of safety. QS equals Q/FOS, where FOS typically ranges from 2.5 to 3 depending on the type of soil and loading conditions. Limitations of Terzaghi's analysis. Soil heterogeneity. The theory assumes homogeneous soil, which may not be accurate for real-world conditions. Foundation shape. The equation is primarily applicable to strip footings, and modifications are needed for other shapes like square or circular footings. Depth effect. The theory is best suited for shallow foundations, and may not be accurate for deep foundations. Question 4. Given data, footing type, O strip footing, 1m wide O square footing, 3m times 3m soil properties, O unit weight of soil equals 1.8 t/m superscript 3 equals 18 knots per cubic meter. O cohesion equals 2 t/m superscript 2 equals 20 knots per square meter. O angle of internal friction equals 20 degrees. 9. O bearing capacity factors. NC equals 17.5, NQ equals 7.5, N gamma equals 5. Answers. Step 1. Terzaghi's ultimate bearing capacity formula Q equals CNC plus QNQ plus 0.5 gamma BN gamma, where Q equals gamma dF is the overburden pressure at foundation depth. B is the width of the foundation. Since the depth of the foundation dF is not given, we'll assume dF equals 1.5 m. Q equals gamma dF equals 18 times 1.5 equals 27 kN/m superscript 2 Q. Step 2, calculation for strip footing using the formula, Q equals plus Q equals 350 plus 202.5 plus 45 Q equals 597.5 knots per square meter. Step 3, calculation for square footing, Q equals plus Q equals 350 plus 202.5 plus 135 Q equals 687.5 knots per square meter. Step 4, calculate safe bearing capacity using factor of safety equals 3. QS equals Q/FOS for strip footing, QS equals 597.53/3 equals 199.2 kN/m superscript 2 for square footing, QS equals 687.53/3 equals 229.2 kN/m superscript 2. Final answers. 10. Ultimate bearing capacity for strip footing, 597.5 knots per square meter. Ultimate bearing capacity for square footing, 687.5 knots per square meter. Safe bearing capacity for strip footing, 199.2 knots per square meter. Safe bearing capacity for square footing, 229.2 knots per square meter. Case 2-5, explain the Rankine's theory of active earth pressure for submerged backfill. Answers: Rankine's theory of active earth pressure for submerged backfill. Introduction to Rankine's earth pressure theory. Rankine's theory provides a simplified method to calculate active and passive earth pressures acting on a retaining wall. It assumes that the soil is homogeneous, isotropic, and obeys the Mohr-Coulomb failure criterion. When the backfill is submerged, the presence of water reduces the effective stress, which affects the active earth pressure exerted on the retaining structure. One concept of active earth pressure in submerged backfill. Active earth pressure. When the wall moves away from the backfill, the soil expands, and the lateral pressure reduces to its minimum value, known as active earth pressure. The total pressure in submerged conditions consists of 1. Effective pressure due to submerged soil. 2. Hydrostatic pressure due to water. 2 assumptions of Rankine's theory. 1. The soil is cohesionless. 2. The backfill surface is horizontal. 3. The wall is smooth and vertical. 4. The failure plane is inclined at an angle from the horizontal. 5. The soil mass is in a plastic state at failure. 3. Calculation of active earth pressure for submerged soil. Total active earth pressure. 11. For submerged soil, the total pressure has 2 components. 1. Effective pressure due to submerged soil. Sigma equals gamma z. Where gamma equals submerged unit weight of soil equals gamma W equals gamma equals total unit weight of soil. Gamma W equals unit weight of water. Z equals depth of soil. Hydrostatic pressure due to water. U equals gamma WZU. The total lateral pressure at depth Z is sigma A equals Ca gamma Z plus gamma WZ, where Ca equals Rankine's active earth pressure coefficient. Ca equals 1 plus sin/1 sin. For distribution of active earth pressure, the active pressure distribution increases linearly with depth. The total active force per unit length of the wall is found by integrating over the height h. Pa equals 1/2 Ca h caret 2 plus 1/2 gamma W h caret 2. The first term represents the effective stress component. The second term represents the hydrostatic pressure component. The resultant force acts at h/3 from the base. 5. Effect of submersion on earth pressure. Reduction in soil strength. The effective stress decreases due to water pressure. Increase in lateral thrust. Water pressure adds to the total force acting on the wall. 12. Risk of instability. Retaining walls need drainage provisions to prevent excessive buildup of poor water pressure. Question 5. calculate the active earth pressure given that C equals 20 knots / n unit weight of the soil being 20 kN/m for a vertical cut of depth 3 m. The soil is cohesionless soil. Answers: given data, cohesion equals 0 unit weight of soil equals 20 knots per cubic meter, depth of vertical cut equals 3 m, angle of internal friction equals not provided. Since cohesionless soil is given, the active earth pressure is calculated using Rankine's theory. Step 1. Rankine's active earth pressure coefficient for cohesionless soil. Rankine's active earth pressure coefficient is Ca equals 1 plus sin/1 sin. Since phi is not given, if provided, we can compute Ca using the above formula. Step 2. Formula for active earth pressure. The lateral active pressure at any depth z is given by sigma A equals Cas. The total active force per unit length of the wall is Pa equals 1/2 Ca h caret 2. Substituting values. Pa equals 1/2 Ca 2, Pa equals 30 Cac n/m. The active earth pressure force per unit length depends on the value of phi. If you provide the angle of internal friction, I can calculate the exact value of Ca and Pa. 13. Question 6. Design a reinforced concrete rectangular combined footing for two columns A and B located 3.6 m apart. The sizes of column are 400 mm x 400 mm and 600 mm x 600 mm, and the loads on them are 1000 knots and 1500 knots respectively. The projection of the footing beyond the axis of the column is limited to 590 mm. The limiting bearing capacity of soil is 420 knots per square meter. Use M15 concrete and Fe 415 steel. Answers: given data, columns, column A, 400 mm times 400 mm with load 1000 knots, column B, 600 mm times 600 mm with load 1500 knots, column spacing, 3.6 m, footing projection beyond columns, 590 mm, bearing capacity of soil, 420 knots per square meter, material properties, concrete, M15 steel, Fe 415. Step 1. Determine the required footing size, the total load on the footing. P equals PA plus PB equals 1000 plus 1500 equals 2500 knots. The required footing area. A equals P slash XAF equals 2500 slash 420 equals 5.95 square meters. Footing width, the total length of the footing. L equals column spacing plus 2 times projection. L equals 6 plus 2 equals 4.78 m. The width of the footing. B equals A slash L equals 5.95 slash 4.78 equals 1.245 1.25. Thus, we assume footing size, 4.78 m times 1.25 m. 14. STEP2, check bearing pressure, the actual bearing pressure. Q equals P slash A equals 2500 slash equals 418 knots per square meter. Since Q is less than the safe bearing capacity, the assumed size is acceptable. Step 3. Locate the centroid of the footing to balance the loads. The footing must be centrally placed under the resultant load. Taking moments about column A, x equals slash 5400 slash 2500 equals 2.16 m. Thus, the centroid of the footing should be 2.16 m from column A. Step 4. Thickness of the footing to resist punching, shear and bending. We determine the depth. Punching shear, check the critical perimeter for punching around column A. U equals 4 equals 1.6 plus 4 do equals 4 equals 1.6 plus 4 d. Punching shear force, VU equals PA, Q times accurate equals U times d. Shear stress. Tau V equals VU slash U times d. Since tau V less than or equal to tau C, we determine ddd to satisfy this. Bending moment, check maximum bending moment occurs at the center. M equals QL caret 2 slash 8 from IS 456, the effective depth ddd is selected to ensure m less than or equal to RBD_2 we assume d 500 mm and check for adequacy. 15. Step 5. Reinforcement design using Fe 415 steel and M15 concrete. Reinforcement is provided along both directions. Main reinforcement is equals m/0.87 FYJD. We select suitable bars based on spacing and development length. Distribution reinforcement, lighter reinforcement to handle temperature and shrinkage stresses. Final footing design, footing size, 4.78 m x 1.25 m thickness, 500 mm main steel, Phi 20 mm at 150 mm C/C top steel, Phi 12 mm at 200 mm C/C concrete cover, 50 mm. Question 6. Explain the design aspect of trapezoidal combined footing. Answers. Design aspects of trapezoidal combined footing. 1. Introduction. A trapezoidal combined footing is used when two columns carry unequal loads and the resultant of the loads does not lie at the center. This type of footing ensures that the soil pressure is uniformly distributed by providing a larger footing area under the heavily loaded column. Two situations where trapezoidal footing is used: when two columns have different loads. When the property line restricts the use of equal projections beyond both columns. When a rectangular footing would result in an unequally distributed soil pressure. 3 Design considerations. 16. The goal of trapezoidal combined footing is to maintain uniform soil pressure while keeping the resultant load within the footing area. The design involves 1. Footing shape and dimensions. The footing has two different widths, a narrower width under the lightly loaded column, a wider width under the heavily loaded column. The length of the footing is determined by ensuring the centroid of the applied loads coincides with the centroid of the footing. 2. Area of footing. The total required area of the footing is determined using the safe bearing capacity of soil. A equals P1 plus P2/safe. 3. Location of centroid. The centroid of the footing must align with the resultant load, x equals P1 times D/P1 plus P2, where P1 and P2 are column loads. The distance between columns. For shear and bending moment calculations, the footing must be thick enough to resist shear and bending stresses. Critical sections are at the column face for punching shear, at midspan for bending moment. 5. Reinforcement design. Main reinforcement is provided at the bottom to resist bending moments. Distribution reinforcement is provided at the top to prevent temperature and shrinkage cracks. 4. Advantages of trapezoidal combined footing. Efficient use of materials, reducing unnecessary concrete and reinforcement. 17. Ensures uniform soil pressure, preventing differential settlement. Ideal for constrained site conditions, such as near property lines. Question 7. State the design requirement of a foundation. Discuss brightly the causes of settlement. Answers. 1. Design requirements of a foundation. A foundation is the lowest part of a structure that transfers loads to the soil. A well-designed foundation should meet the following requirements. 1.1 Strength and stability. The foundation should be capable of safely carrying and transmitting the loads of the structure to the soil without failure. It must be able to resist shear failure and ensure overall stability. 1.2 Adequate load distribution. It should distribute the loads evenly over a sufficient area of soil to avoid excessive settlement. The soil bearing pressure should be within the safe bearing capacity of the soil. 1.3 Minimum settlement. The foundation should be designed to have minimum differential settlement to avoid cracks and structural damage. It should maintain the serviceability of the structure. 1.4 Resistance to ground movements. It should be able to withstand expansive soil movement, earthquakes, and vibrations from nearby structures or traffic. Proper anchoring should be provided in unstable soils. 1.5 Durability. The foundation should be protected against environmental effects such as frost action, water table fluctuations, and chemical attacks. Waterproofing should be done to prevent foundation deterioration. 1.6 Economy and constructability. The foundation should be economically feasible and easy to construct using locally available materials. The design should minimize excavation costs and construction time. 18. 2 causes of settlement of foundations. Settlement occurs when the foundation sinks into the soil due to soil compression or displacement. It can be classified into 2 types, uniform settlement and differential settlement. 2.1 Causes of settlement. 1. Weak or compressible soil. Loose, soft clay or organic soils compress over time, causing excessive settlement. Peat and highly compressible silts are especially problematic. 2. Excessive structural loads. If the applied loads exceed the safe bearing capacity of soil, excessive settlement occurs. Uneven load distribution can cause differential settlement. 3. Fluctuations in the water table. A lowering water table can cause soil shrinkage and lead to foundation movement. High water tables in sandy soils can cause liquefaction during earthquakes. 4. Poor compaction of soil. If the soil is not properly compacted before construction, voids may collapse over time, causing settlement. This is common in fill soils or reclaimed land. 5. Vibrations from construction or traffic. Vibrations from pile driving, heavy machinery, or road traffic can lead to soil densification and settlement. 6. Tree roots and soil shrinkage. Trees absorb moisture from the soil, causing it to shrink and settle unevenly. Clayey soils are particularly prone to shrinkage due to drying and wetting cycles. 7. Erosion of soil under foundation. Water seepage or poor drainage can wash away soil beneath foundations, leading to loss of support and settlement. 19. This is common near rivers, coastal areas, and poorly drained sites. 8. Mining, excavation, or underground works. Underground activities such as tunneling, mining, or sewer line installation can cause voids beneath a foundation, leading to settlement. Question 7. Write down the procedure to conduct standard penetration test. Answers. The standard penetration test is a widely used in situ soil test to determine the bearing capacity, relative density, and strength properties of soil. It is conducted in boreholes during geotechnical investigations. 1. Equipment required: drilling rig, to create a borehole. Split spoon sampler, a cylindrical tube used for soil sampling. Drop hammer, used for driving the sampler. Drill rods, to lower the sampler into the borehole. Anvil and guide rod, ensures the correct drop height of the hammer. Measuring tape, to measure penetration depth. 2. Step-by-step procedure. Step 1. Preparation of borehole. A borehole is drilled using rotary or percussion drilling to the required depth. The borehole diameter is typically 100 mm to 150 mm. Step 2. Lowering the split spoon sampler. The split spoon sampler is attached to drill rods and lowered to the testing depth. Step 3. Driving the sampler. A 63.5 kg hammer is dropped from a height of 750 mm. The hammer is repeatedly dropped, driving the sampler into the soil. The penetration is recorded in 3 stages of 150 mm each, for a total of 450 mm. Step 4. Recording the blow count. 20. The number of blows required to drive the sampler for each 150 mm is recorded. The total number of blows for the last 2 150 mm increments is the SPTN value. Step 5. Collection of soil sample. After penetration, the sampler is removed, and the soil sample is extracted for classification and laboratory tests. Step 6. Repeat the test at different depths. The test is conducted at regular depth intervals depending on the project requirements. 3. Interpretation of results. The SPTN value is used to determine O relative density of granular soils, O consistency of cohesive soils, O bearing capacity of the soil, O liquefaction potential in seismic zones. N value soil condition 0 to 4 very loose 11 to 30 medium dense 31 to 50 dense 50 very dense. 4. Limitations of SPT not suitable for very soft or very hard soils. Results can be affected by operator errors and equipment conditions. Provides approximate soil properties and should be used with other tests. Question 8. Write short notes on forces acting on pile cap and under-reamed piles. Answers. 1. Forces acting on a pile cap. A pile cap is a thick reinforced concrete slab that rests on a group of piles, distributing the superstructure loads into the piles. The following forces act on a pile cap. 21. 1.1 Vertical loads. These include dead loads and live loads. The pile cap transfers these loads to the piles, which then distribute them to the soil. 1.2 Lateral loads. Wind loads and seismic forces cause horizontal forces on the pile cap. These are transferred to the piles and resisted by pile group action and lateral soil resistance. 1.3 Bending moments and shear forces. The pile cap experiences bending moments due to eccentric loads or unequal pile reactions. Shear forces occur due to the load transfer mechanism from the structure to the piles. 1.4 Uplift forces. In some cases, uplift forces occur due to wind or buoyancy effects. Tension piles may be used to counteract these forces. 1.5 Differential settlement forces. If piles settle unevenly, the pile cap may experience stress concentrations, leading to cracking or failure. 2 Forces acting on under-reamed piles. Under-reamed piles are specially designed piles with bulb-like enlargements at specific depths to increase bearing capacity and reduce settlement. 2.1 Axial loads. Compressive loads. The superstructure load is transferred to the pile, which then distributes it to the soil through end bearing and skin friction. Tensile loads. In structures like towers, chimneys, and transmission lines, under-reamed piles resist uplift by mobilizing skin friction and bulb resistance. 2.2 Lateral loads. Structures in seismic zones, bridge piers, and retaining walls experience significant lateral loads. The enlarged bulbs provide additional lateral resistance. 22. 2.3 Bending moments. Bending moments develop due to unequal soil pressure around the pile or lateral loads from wind, waves, or seismic activity. 2.4 Negative skin friction. In soft clay or expansive soils, the downward movement of surrounding soil exerts a drag force on the pile, increasing the effective load. Question 8. Discuss briefly earth pressure at rest, active earth pressure and passive earth pressure with expression and neat sketch. Answers. Earth pressure refers to the lateral force exerted by soil on retaining structures such as walls, foundations, and sheet piles. It varies based on soil movement and confinement conditions. The 3 main types are 1. Earth pressure at rest. 2. Active earth pressure. 3. Passive earth pressure. 1. Earth pressure at rest occurs when soil is not allowed to move laterally. The lateral pressure remains equal to the natural horizontal stress in the soil. It is determined using the coefficient of earth pressure at rest, K0 equals 1 sin where phi equals angle of internal friction of the soil. K0 is typically 0.4 to 0.6 for granular soils and 0.6 to 0.9 for cohesive soils. Graphically, it is represented by a triangular pressure distribution acting on the retaining wall. 2. Active earth pressure occurs when the retaining wall moves away from the backfill, allowing the soil to expand. The soil mass undergoes shear failure, leading to minimum lateral pressure on the wall. 23. The active earth pressure coefficient is given by Ca equals 1, sin/1 plus sin. The active earth pressure at any depth z is sigma A equals Ks, where gamma equals unit weight of soil, z equals depth below the surface. Graphically, active pressure increases linearly from 0 at the top to a maximum at the bottom. 3. Passive earth pressure occurs when the wall moves toward the soil, compressing it. This leads to maximum lateral resistance by the soil. The passive earth pressure coefficient is given by the passive earth pressure at depth zzz is sigma p equals kp gamma z. Graphically, passive pressure also follows a triangular distribution but acts in the opposite direction to active pressure. Neat sketch a diagram illustrating all three earth pressure conditions is shown below. Mark down copy edit earth surface. Active at rest passive wall moves away, no movement wall moves in low pressure intermediate high pressure. Question 9. Explain the concept of ground movement and its causes in the context of construction activities such as excavation, tunneling, and foundation installation. Answers. 1. Introduction to ground movement. Ground movement refers to the displacement, settlement, or deformation of soil and rock due to natural or man-made activities. In construction, ground movement can significantly impact excavations, tunneling, and foundation installations, leading to potential structural failures if not properly controlled. 2 causes of ground movement in construction. 2.1 Excavation-induced ground movement. Excavation removes soil, altering stress distribution and causing movement. The effects include loss of lateral support, retaining walls and adjacent buildings may shift. Ground settlement, soil compresses due to unloading. Heave, the bottom of the excavation may rise due to stress relief. Water table changes, lowering the water table can cause differential settlement. Example, deep excavations for basements in urban areas can affect nearby structures if not properly supported. 2.2 Tunneling-induced ground movement. Tunneling disturbs the surrounding soil and rock, leading to ground subsidence, the formation of a depression above the tunnel. Lateral displacement, sideways soil movement, affecting nearby foundations. Cave-ins or collapses, weak soil or improper support can cause tunnel failure. Example, the London Underground construction required extensive ground monitoring to prevent settlement in historical buildings. 2.3 Foundation installation and soil disturbance. Foundation works alter stress distribution and cause movement due to pile driving and drilling, creates vibrations that compact or loosen the soil. 24. Differential settlement, uneven sinking of a structure due to varying soil strength. Expansive soils, clays swell or shrink due to moisture changes, affecting stability. Example, high-rise buildings with deep foundations can cause settlement in nearby structures if load transfer is not managed. 3 Effects of ground movement on construction. Structural damage. Service disruption. Safety hazards. 4 Mitigation measures. Excavation support systems. Ground improvement. Monitoring and risk assessment. 25. 26.